In this lecture, we're going to talk about the theory of deformation. Now, I teach this in a class on theory of elasticity. But really, this is much more general than just elastic material behavior. This also holds for elastic plastic materials and so forth. And so we're going to take a look at the basic assumptions from a continuum mechanics perspective of what deformation is. This will help set the stage for our discussion of the Green-Saint Venant strain tensor. Now, hopefully you have some background in index notation, as we will start to use this in a little bit more detail, starting with this lecture. So when we talk about deformations, we kind of have an idea of what that means. Something squishes or stretches out or whatever. But from the kind of a more formal definition, we can say that a deformation is a transformation of a continuous body from one configuration to another. So on the left, I have a certain three-dimensional body. A lot of books like to show them just like this. They're kind of weird shapes, potato shapes, but that's supposed to represent any arbitrary general three-dimensional shape. And after some loads are applied to it or things move around, get squished around, then it becomes that second shape that we see on the right. So configuration A may be the starting point, and configuration B may be the final point that it ends up with. There may be intermediate steps in between. We could have started with configuration B and gone back to configuration A. So there's lots of different ways to look at this, but this transformation from one configuration to another is what we're going to call a deformation. Now, our body doesn't have to be solid. Now, in our course in theory of elasticity, we will look at solid bodies exclusively. It doesn't have to be solid, but it has to be a continuum. So it cannot be things that mix easily, like gases. We're not looking at bodies of gases, but the molecules or the atoms or whatever you consider to be your basic constituent of your material need to be close enough together that they can move around when they're deformed, but they don't circulate, mix. So we maintain continuum deformation. Now, there are ways that you can deal with those other situations, but that will not be the subject of this particular course. So let's draw our bodies again, and let's get into a little bit more details about this transformation. So here on the left, I'm going to call this my original configuration. I'll use regular R. In my final configuration, I'm going to use a script R. In our original configuration, we can find a coordinate system, and I'll use x1, x2, and x3. We can express our final shape in that coordinate system, or we can express it in terms of a more general deformed coordinate system. And we'll do this initially, but we're going to relax this a little bit, and we're going to work only in our original coordinate system. So maybe we want to call this xi1, xi2, and xi3. And for any point that we have inside this body, we can call that point P, it will map into another point over on this deformed body, or the second configuration, via this transformation that we're talking about. And we'll give some examples of transformations here in a little bit, some kind of simple ones. Not only does that particular point map to that point, but every point maps to another point. And here's the important part too, is that if you have some points that are what we call in the neighborhood of point P, like nearby, they will also map to points that are nearby neighborhood of point script P. So even though this one is deformed, see it's not quite as circular, they're still pretty close together. So they're not doing that mixing that we talked about. So we'll label this one as our reference. And this one over here is our final. Okay, so just put a few words here. Point P in the reference. Configuration, so that's regular R, is located at x1, x2, and x3 from our coordinate system origin, and it transforms to a point script B in our new configuration, or script R, and its coordinates are xi1, xi2, and xi3. Then the neighborhood of points near regular P transform to points in the neighborhood of script P. Okay, so we can kind of give some structure to this transformation. And the coordinates in the new configuration are functions of the location of the point in the old configuration. In general, it can be that, and it can change with time, so we can put that in here as well. And so xi1 is equal to function of x1, x2, and x3, as well as the other two coordinates in the new configuration. Now, the next step we're going to take is that we're going to make use of the fact that there's a one-to-one correspondence between the points in the reference configuration and in the final configuration. That has some important implications for us, and we'll write those down. So with this assumption that there is a one-to-one correspondence between points in regular R and script R, the reference and the final configuration, the implications of that are that it means that one point cannot go to two different places. One point cannot split into two, and two separate points can't be merged into one single point. That's the basic definition of a continuum. Now, there's an implication of this that we can think of mathematically. If we have these transformation functions xi as a function of x1, x2, and x3, it implies that these functions are invertible. And so we can find, for example, x1 is a function of the final coordinates in general time. And likewise for x2 and x3. So we can go either way. We can start with our reference and go to our final configuration, or with the inverse mapping, we can go from our final configuration and get to our reference configuration. This is invertible and it's one-to-one. Now we're going to talk a little bit about displacements next, and we'll get into something called the Jacobian. I think it'll make more sense once we can talk about displacements. And so in our description of displacements, we could use the curvilinear coordinate system, or we can go back and use our original reference coordinate system. And for our purposes right now, we're going to express both in terms of our original coordinate system. You can do different coordinate systems with appropriate transformations of the coordinate system too. That's a little bit more overhead than we want to take on right now. So Let's say that we have a fixed orthonormal basis for our coordinate system. We're going to use x1 and x2 and x3. I can locate the point P in my original coordinate system, and that was going to be the vector I'm going to call the vector x. From my original coordinate system, I can locate where the point moves to after the deformation, and I'll call that vector xi. And the difference between those two is going to be my displacement. I'm going to call that u. So let's make a little note. And so to make our life a little bit easier, we're going to use our original coordinate system to describe both configurations. And the displacement of a point is going to be given by u is equal to my final minus my initial position. Now, because we can express all of these vectors in our orthonormal basis, we can also write it this way if we want. With components of displacement in my original coordinate system being equal to components of my coordinate vector in my final configuration minus the coordinates of the point in the original configuration times their respective unit normal basis vectors. Now these are the vectors. This is how we would express vectors with an implied summation. And if we were to just look at the components, we could say the components of ui then would be the components of xi minus xi. Now when things will start to get interesting is when different parts of the body can displace different amounts. We can have a gradient in displacements. And this idea of a displacement gradient that can vary in three directions, each component of the vector, three components, can vary in three different directions. 3 by 3, we end up with a 9-term second order tensor. We'll get into those details soon, but we want to talk next about something called the Jacobian. Now, the Jacobian is a term that you may have heard in other classes. If you take a class in finite elements and you look at a three-dimensional solid element and you compute the Jacobian, that represents the volume of that element. And we can do something similar. And the reason why we're going to look at the Jacobian the way that we are is that these equations from xi to x and from x to xi, in order for them to be invertible, and they have to also meet some differentiability conditions, in order for them to be invertible, there has to be a relationship among the partial derivatives of these functions with respect to each of the components. So let me write down the Jacobian, and we'll take it from there. This Jacobian is written as the determinant of the set of partial derivatives. Partial derivative of xi1 with respect to x1 is our first entry. Moving across the first row, partial of xi1 with respect to x2 and partial of xi1 with respect to x3. And likewise for the next two rows in that determinant. More compactly, we can write this as J is the determinant of the matrix formed by taking the partial derivative of xi I with respect to xj, where I and j are free indices. We can take the values of 1, 2, or 3. Now our condition is that the Jacobian can't be equal to 0. We can also have some additional restrictions. If the Jacobian is positive, it must always stay positive. If Jacobian is negative and must always stay negative. Now, in practical purposes for the kind of problems we're going to work, we're not going to end up with negative Jacobians. That would be usually arising from some kind of unusual coordinate system. If the Jacobian were to pass from positive to negative, basically what that is saying is that a small volume of material around our point is turning inside out. And really physically, that's not what we want to have happen for the types of problems that we're going to work. Now, you may also recognize this from something that we've talked about already called the scalar triple product. The scalar triple product of three vectors that compose the sides of a finite element, a three-dimensional solid finite element. If you take the scalar triple product of those, you get the volume of the finite element. Well, this can be effectively thought as a way to make a scalar triple product of very small infinitesimal vectors around a point in our material. And every point in that material can stretch out some, it can shrink, but we can't get it to go to zero volume. We can express the Jacobian in terms of displacements as well. Okay, so we have the determinant of xi, partial derivative of xi with respect to xj. Since we know that what did we write it? We wrote the displacement is equal to the final minus the initial position. The final position can be written in terms of the initial position plus the displacement. So on the top of this expression, we can have the partial derivative of xi plus ui. And on the bottom, we have the part with respect to xj. We can expand this. We have the partial derivative of xi with respect to xj plus the partial derivative of ui with respect to xj. And this term right here, partial derivative of xi with respect to xj, is only going to give a value of 1 or 0. It's going to be equal to 1 if I and j have the same numbers for their subscript. It's going to be equal to 0 otherwise. So that indeed is our Kronecker delta. The symbol that we defined previously. And we can write this as the partial of ui with respect to xj. And there's even a little bit more compact notation that we can use. Instead of having the partial derivatives written explicitly, we can write ui comma j, where the comma denotes partial differentiation with respect to coordinate. And we'll use this notation from time to time. It doesn't just have to be in that particular instance, but anything that we have, any expression, if we put a comma, whatever, then it's going to be the partial derivative of that with respect to x sub whatever subscript that happens to be. So if we were to do this, then let's write down our first term. Psi1 would be equal to x1 plus u1. The partial derivative of psi1 with respect to x1 would be equal to 1 plus the partial derivative of u1 with respect to x1. And so if I had psi2, that would be equal to 0 plus u2. And the partial derivative of psi2 would be, oops. Hang on here a second. So psi1 would be equal to x1 plus u1. Partial derivative of psi1 with respect to x1 is equal to 1 plus partial of u1 with respect to x1. Partial derivative of psi1 with respect to x2, that's what I wanted to do, would be equal to 0 plus the partial derivative of u1 with respect to x2. And I'll let you fill out the rest of this matrix, but as we go through each of these terms, what we'll find is that we'll get 1 on the diagonal of each of these terms with displacements, and then the partial derivative of the other displacements on the off-diagonal terms. So let's write down that full Jacobian. And there we have it here in terms of displacements. Now, which form of the Jacobian you use depends on what information you're given. If you're given the transformation equations from original to final, you're given the xi equations in terms of x, then it's probably easiest to use that top equation. However, a lot of times in our class, we're going to be given displacement equations in the original positions, and we may not be terribly concerned about the final positions, so we want to use the bottom form of the Jacobian. One common mistake that I've seen students do is to leave off the 1 on the diagonal terms. But if you think about where that comes from, it makes a lot of sense. So if you notice, I have the 1 plus the partial derivative on these 3 terms on the diagonal, and then otherwise I just have the partial derivative of the mixed displacement term with respect to position. So don't forget the 1. So let's talk about some rigid displacements. So if we think of our body that's sitting here and we're in our coordinate system that we have, and we have our R, and here's our point P, and that point P is located at a certain coordinate triple. And I could move it if I want, but if I don't move it, that is still a displacement. We can think of that as a degenerate displacement. So if my function for xi1 is xi1 is equal to x1, xi2 is equal to x2, and xi3 is equal to x3, when we evaluate our Jacobian, we'll end up with 1 on the diagonal and 0 everywhere else. And that's a pretty easy one to evaluate. We're going to end up with 1. So at that particular point, and if everywhere in that body does not move, then volume is conserved. The Jacobian is a measure of the volume. Okay, so that's a pretty simple type of displacement. Well, there's another type of displacement that we can have. Let's say that xi1 is equal to a constant, xi2 is equal to another constant, and xi3 is equal to yet another constant. Well, when we take the partial derivative of this with respect to x, we get 0, but yet we have 1 along the diagonals. Or C1, C2, and C3. If we evaluate it as the partial derivative of xi I with respect to x j. Oh, my apologies, I wrote the wrong term down here. I was speaking in terms of displacements. And in terms of displacements, I would have 1 along the diagonal still. If it's a rigid displacement, it doesn't expand. And so we can define a rigid translation as a situation where the displacement of every single point is the same. It's maybe easier if I show this just going horizontally. But the UI components are the same for every point. And lastly, we can also define a rigid rotation. And that is, if we can define our axis of rotation, all points move through the same angle about that axis of rotation. A general rigid body motion can consist of translation and rotation, and those can also be decoupled. You can take it as a two-step, first pure translation and then rotation, or vice versa. There's some other interesting things that come about because of our assumptions of continuum behavior, and we'll just talk about these and kind of see how they make sense. This is something you probably dive into a little bit more detail in a formal class in continuum mechanics. But if you have a point that is on the surface of our body, it will map into a point that's on the surface of the deformed body. If you have a point that's on the interior of the body, those points will be mapped to points on the interior of the deformed body. Okay, so we're not allowing the boundary to mix with what's inside. That's kind of interesting. If you think of it like a soft football that you can squish, our continuum assumption is that the points on the outer skin of that football stay on the outer skin even though you have it squished up. And there's some related axioms, something about if you have a line, points on a line will remain on a line, and those kind of interesting things that you can say about continuum deformations as well. Again, we won't go into that level of detail, but we need enough background now to be able to talk about our next step, which is the change in length of a line segment inside of our body. We're going to talk about deformations, and that'll lead us to our green St. Venant strain tensor.